Good morning, distinguished judges and members of Informs. I am Fred Deschamps, Vice President, Global Revenue Generation for the Carlson Rezidor Hotel Group. We're thrilled and we're honored to be a finalist for this year's France Edelman Award. Let me also congratulate our co-finalists for their projects. Together, we're furthering the application of operations research to some meaningful management challenges. Our presentation today shows how we applied advanced operations research techniques to improve our ability to manage demand and optimize prices in response to significant changes in the marketplace. The Stay-Night Automated Pricing, or SNAP project, that we will describe is one of the largest and longest running in our company in any of our commercial areas. 4 years in the making at a cost of at least $10 million. We basically started from scratch. Prior to this project, our hotels were maximizing revenue in a manual way, unaided by any decision support tools. We consider this project one of our largest successes, as measured by the impact it's had on the profit margin of our hotels and of the company. Let me briefly introduce our company to you. The variety of the hotel types and the geographic spread of these hotels have deep implications for the solution we needed. We're a family-owned and very global hotels company. We have 1,300 hotels in operation and development worldwide, with a concentration in Western Europe and North America. We are the largest hotel company in India, Western Europe, and Russia. So overall, this makes us the 9th largest hotel company in the world. The implication of this global footprint is that any solution we deploy has to work worldwide. It also has to be available with fresh input data on the normal, local daily work schedule anywhere in the world. We operate 6 distinct global brands. Each one offers a different level of service and targets a different customer. Our hotels portfolio is a balanced mix of upscale and mid-scale hotels, with about 60% of our room capacity in upscale or higher. The implication is that our revenue maximizing solution would have to perform equally well across a range of service level expectations and the corresponding price ranges. Let me briefly give you a sense of our brands. Our mid-scale brand offers value with caring and consistent service. Our upper mid-scale brand adds an element of design in urban locations. Our upscale brands includes a number of full-service resorts with health and entertainment facilities. Our upper upscale brand targets the business traveler, and our luxury brand caters to the affluent looking for a unique hotel with eclectic design. Our hotels vary greatly in size, anywhere from 30 rooms in Monaco, Wisconsin, to 1,200 rooms in Moscow. But 50% of our hotels have 110 rooms or less. These are typically hotels in our mid-scale brand, and many are operated as a family business. These hotels depend heavily on getting their fair share of revenue, yet have limited resources to dedicate to revenue management. The implication for us is that while any solution needs to address the typical large and complex hotel, it also needs to address the smaller hotel with limited staff. Starting in 2006, we found ourselves facing significant new challenges in the marketplace. The main challenge we have is that distribution channels are no longer a good way to divide customers into groups and charge them different rates. The internet is what changed everything. Business-oriented travel management companies and leisure-oriented travel agencies and brand webs moved to a common distribution platform and started reaching into each other's customer bases. Travel management companies started offering leisure programs on their websites, and online agencies and brand webs expanded into online travel management programs. Then, search engines drove that transparency even further by aggregating all the online rates from all channels into single, easy-to-use interfaces, showing price as the most prominent differentiator between products. The implication for us is that unless we find a new way to set rates, in this transparent environment, all of our demand could gradually slip to the lowest rate. We needed to find a way to set prices based on what the customer is really willing to pay, regardless of how and why they purchased the rate. We decided that our solution would first address the transient rates, the rates most affected by this transparency. Transient rates are not locked in corporate contracts and fluctuate with demand and competition, and represent about 53% of room nights globally. Another challenge we faced is that hotels are rarely full. The industry average occupancy rate has hovered around 60% for the last 7 years, which means that hotels rarely book to capacity. Traditional revenue optimization methods rely on situations where demand exceeds capacity to discriminate against lower rates and hold back capacity for the higher rates. We wondered if there was a different solution that would work equally well whether the hotel has excess demand or not. In 2006, each hotel had its own manual approach to setting rates with no demand forecast or revenue maximization based on competitive rates and market demand. Hotels were often chasing each other's prices, whether it was the right price or not. Or hotels would lock into the lowest rate to ensure that they could not be undersold. Or hotels would simply stick to a traditional weekday, weekend flat rate structure. So these challenges drove us to consider an approach to revenue optimization that would center solely on the customer's willingness to pay. Traditional methods would have considered rates as a given and decided how many rooms to allocate to each rate. The approach we took with Snap was to vary the rates based on customer elasticity at each price point, thus controlling demand to the hotel. To develop this solution, we turned to a partnership with JDA Software Group. Let me introduce Helin Pekun to take us through the solution.
Thank you, Fred. Given the business challenges that Fred described, we came up with a checklist of requirements for designing a revenue optimization solution that could address Carlson Rezidor's needs. In the next slides, I'm going to explain how we addressed each of these requirements. Before I get into the details, I would like to show you a holistic view of the conceived solution. The solution consisted of several components. Demand forecasting to gain visibility into the effects of seasonality and special events, micro-response modeling to understand customers' price elasticity, and competitive modeling to incorporate competitor prices directly into the heart of optimization. Price optimization consumed the output from these components, as well as various constraints such as remaining inventory, length of stay effects, and business rules, and recommended stay night prices. Going back to our checklist, the first requirement was to provide demand forecasts, not only as an input for optimization, but also to bring demand visibility, which Carlson Rezidor could use in other activities, such as targeted marketing initiatives. We decided on a forecasting horizon of 120 days, given that most of the hotels receive the majority of their retail bookings within that time frame. After analyzing demand patterns from historical reservation data, we chose the lowest level of forecasting, which we refer to as the Demand Forecasting Unit, or DFU, to be by hotel, rate segment, length of stay, day of week, and booking interval. A forecast was to be generated by each DFU and arrival date. The length of stay patterns that we forecast were those that were observed historically. We created 10 to 12 telescoping booking intervals, narrower closer to the arrival date and wider further out, to understand the booking curve and the expected number of rooms remaining to sell. Without the booking interval in the DFU definition, we would only be able to use the bookings from past arrival dates whose booking curves were already completed. However, with the booking interval in the DFU definition, we could use the booking information from future arrival dates utilizing the closed booking intervals. We had several forecasting methods at our disposal, but we chose multiple linear regression for a quick ramp up to better forecasts. Multiple linear regression gave us the flexibility to model the effects of seasonality in the form of Fourier series, in addition to the effects of causal factors such as special events like conventions or sporting events and holidays. As an input for forecasting, Carlson Rezidor systematically collected past and future special event and holiday data. Although the DFU level we defined constitutes a direct input for price optimization, it could also result in a data sparsity problem. Therefore, we defined a high level or a parent DFU as an aggregation of the optimization DFUs by length of stay and rate segment. This also helped us define a higher number of regression terms for the parent DFU to better capture seasonality effects. After we executed demand forecasting at both the parent and child levels, we then reconciled forecasts via top-down proportion distribution approach, such that the total forecast across all the child DFUs equaled the forecast for the parent DFU. The next requirement was a solution that could provide meaningful recommendations not only on high demand but also on low demand nights. A traditional revenue management approach would work best on constrained nights. In other words, for any nights where demand is expected to hit or exceed capacity, the bid price or the hurdle rate, which represents the value of an additional unit of capacity, would be non-zero. This could be used as a guideline for the minimum price to charge. However, for all unconstrained nights, the hurdle rate would equal zero, providing no insight on how to price demand. On the other hand, through a price-sensitive demand model, we can find the optimal price to charge to maximize the revenue, which is an approach that would work on both high demand and low demand nights. One design possibility for a hotel price optimizer is to recommend a price for each length of stay and rate segment. However, we designed our optimizer to recommend a price for each stay night directly. Let me illustrate the complexity differences between the two approaches. In the hotel world, there are a variety of prices to optimize, which not only increases the complexity of optimization, but also is difficult to review and digest by the time-pressed hotel operators. Namely, based on Carlson Rezidor data for a given hotel, we have 7 rate segments, 120 arrival dates, 10 booking intervals, and on the average 6 length of stay patterns, which makes a total of 50,400 combinations. In order to decrease the optimization complexity and reduce the workload for the users, we first utilized a rate menu relative pricing concept, where the prices of each rate segment can be tied to the base rate through a menu of additive and multiplicative offsets. For example, the rate codes, which on the average were discounted 20% off of the base rate, were grouped into a 20% off rate segment. Moreover, instead of optimizing a different price for each length of stay, we decided to optimize stay night prices directly. The length of stay price would then be given by an aggregate function, such as the sum of each of the stay night prices that were touched. The rate menu, along with the stay night pricing, significantly reduced the dimensionality, namely to 1,200 rates to optimize per day for each hotel. Hoteliers were sensitive about day-to-day fluctuations, so the next requirement was to control or dampen such fluctuations. At this point, let me present the price optimization formulation to explain the different components of the optimization. The objective is to maximize revenue from all DFUs, that is, arrival date, length of stay, rate segment combinations, where the revenue term includes the DFU price as a function of the stay night prices via the rate menu, an optional unit cost, such as a variable cost of maintaining the room, and an optional ancillary revenue, such as the fixed food and beverage expense. So we maximize the revenue, less penalty terms, one of which is to minimize the price fluctuations from the current price, which is defined only for the current booking interval or the immediately actionable price recommendation. The constraints define the evolution of the bookings along the booking curve, considering the estimated probability of survival or cancellation, price-sensitive demand as a function of the forecasted baseline demand, price elasticity, and the DFU price with respect to a reference price, which can be defined as the price against which customers compare the offered price, projected trajectory of bookings constrained by capacity plus an optional overbooking factor, and business rules to bound the price changes in 2 ways, an absolute minimum and maximum, as well as a threshold or the relative change from the current price. Note that optimization considers not only the price to charge today, but how the prices should change until the arrival date to be able to capture more price-sensitive customers further away from the arrival date and less price-sensitive customers closer to the arrival date. In that respect, we also defined monotonicity constraints to recommend a non-decreasing price profile with the flexibility to limit the number of allowable price change points along the booking curve, which further helps to reduce the dimensionality of optimization. This formulation gives us a network optimization problem because each stay night on the horizon is connected to each other via length of stay, and the demand for a given stay night is the sum of the demand from arrivals on that date as well as arrivals from previous dates that touch that stay night. Therefore, a change on one stay night's rate affects the demand for other stay nights and their pricing decisions. We chose a linear price demand curve, which helps limit extreme price recommendations, as in the case of a constant elasticity model, and also led to a quadratic programming formulation, which enabled the usage of the commercial Cplex solver, a tool widely used in industry. As Carlson Rezidor did not have discrete or special pricing requirements, the solution did not require a mixed integer programming formulation and recommended floating point prices. The solution was targeted for transient rate segments, and non-transient rates were beyond the scope of the price optimization. However, they were still accounted for within the solution. The unconstrained demand for negotiated rate segments for which prices were fixed via other mechanisms was accepted or rejected based on their revenue contribution. Group demand was forecasted, and each hotel allocated a certain portion of the capacity to a group block, which was decremented from the availability that the price optimization solution used. Optimization was supported by a discrete time step simulator to estimate the projected bookings to come and revenue at the current versus recommended rates. This gave the users a measure of the expected behavior and benefit should the recommended rates be implemented. Another requirement of the solution was to keep rates in line with the marketplace. As customers could shop for rates online, the solution also needed to understand what rates were available from the competition. Daily price shops were collected by third-party vendors, screen scraped from brand websites or online travel agency sites. Shopping span and frequency for each hotel's competitors were based on market pricing volatility. After the shops were cleaned and hole filling was applied for unavailable or unretrievable rates, the rates were used in construction of a market reference price, or MRP, to represent the price of the alternatives available to the customer in terms of the competitor rates. Carlson Rezidor preferred to use a weighted average method for this construction, where users could assign a weight to each of their competitors. Afterwards, this MRP was used directly in the price-sensitive demand function with an optimization in place of the reference price. We quickly saw the importance of selecting the right competitor or comp set, not to bias the price recommendations. Identifying true competitors could especially be a challenge when hoteliers were left to select their own competitors, using conventional wisdom that might motivate an economy hotel to select a full-service hotel in the comp set due to simply proximity. Based on this analysis, we formalized a two-step approach for the comp set selection. First, Carlson Rezidor revenue optimization specialists selected a superset of competitors for each hotel, examining attributes such as location, amenities, and service, and identifying those that most closely aligned with the hotel's own offerings. This is referred to as score-based benchmarking, where each competitor is assigned a score based on its attributes, and the ones that get a score closest to the reference hotel are selected in the superset. As for the second step, JDA developed an automated weight estimation module based on constraint regression principles, which analyzed price shops over time and recommended weights and price differentials, median price differentials, for each competitor, such that the sum of the competitor weights added up to 1. This data-driven strategy further reduced the superset to typically 5 to 6 competitors, whose pricing trends most closely correlated with the hotel's own pricing trends. Here, we can see a real example where a user thought of all 5 competitors as being equally important in pricing decisions, which would lead to an incorrect inference as the hotel being priced too high as compared to the market rate. When we apply the constraint regression techniques to analyze the price shops over time, we see that only 3 out of these 5 competitors had closer pricing trends to the own property, and thus the computed MRP gets in line with the own pricing trends, avoiding a bias in the recommendations. We designed this approach to be able to estimate different weights by season or weekday versus weekend patterns. The other requirement was to be able to understand customers' price sensitivity or price elasticity, which is measured by the percent change in demand for a percent change in price. Understanding the price elasticity of customers is critical in making correct pricing decisions. Regression techniques are standard in estimating price elasticity. However, such methods require historical data. Since the price-sensitive demand is a function of both on price and MRP, competitor price shops had to be accumulated over time before statistical estimation techniques could be used. Moreover, for new properties with little or no data, and properties with rare historical price changes, demand-price response could not be reliably estimated. Therefore, we devised a quick-start elasticity computation to address these challenges. This optimization-based method distributes elasticities across the rate segments consistent with business expectations, according to an ordering of rate segments such that higher valued rate segments would be less price sensitive and lower valued rate segments would be more price sensitive, keeping the elasticities within a reasonable interval and centered about a specified value. We weighted the distribution by the total expected demand for each rate segment such that the price optimizer would not have an overall bias to either raise or lower the rates over the forecast horizon. There are other analytical aspects of the solution that I have omitted for the purposes of brevity. So I now hand the floor to my colleague Suresh Acharya to discuss some of the implementation and development aspects. Thank you.
Thank you, Pelin. In the next segment, I'm going to address two of Carlson Rezidor's requirements that have direct architectural implications. The first requirement is fairly straightforward, that rate recommendations be available for a user to review at 8 a.m. local time, no matter where that user sits around the globe. The second requirement needs a bit of background. Some large hotel chains have extensive OR and IT departments that develop custom software to meet that hotelier's specific needs. Carlson Rezidor espoused a different philosophy, opting instead for industry-standard, best-of-breed solutions that evolve with market trends and are enhanced based on user group feature requests. To expand on the solution overview diagram Pelin showed earlier, the Carlson Rezidor implementation involves supporting both a responsive environment for users while achieving high-volume, complex computational results. On the left in this diagram, we illustrate some of the forecasting and optimization processes that need to be executed. The processes shown are the major ones, but there are dozens of other processes that must also execute to support these. Users occasionally manage system parameters such as competitor weights, autopilot settings, display options, and so forth. But the main user interaction with Snap involves reviewing rate recommendations on a daily basis. The requirement Carlson Rezidor presented was that a user be able to review recommendations by 8 a.m. local time wherever they sit. The various other processes could be moved around during the day or night as necessary to achieve this goal. So let's get a feel for this plan centrally, review locally operation. For Carlson Rezidor, all computational processing occurs centrally in Omaha, Nebraska. The wall clock on the top left shows Omaha local time. The alarm clock shows 8 a.m. in the local time of various zones, representing the beginning of the day for Snap users. For instance, at 6 p.m. Omaha time, the system should have made results available for users in Asia as they head out to work, while continuing to optimize results for Europe while it is asleep, and support heavy interactions and rate uploads in North America. People sleep, people wake up, people go to work. However, the machine needs to move on. So, how does this distributed processing become a reality? This was achieved by creating 7 geographical zones with different zones performing different processing at different times of the day. Next, we will see the enterprise architecture that enables this. In order to be successful, we knew that the Snap system had to address 3 key areas: performance, scalability, and failure recovery. The J2EE-based JDA enterprise architecture, with its distributed infrastructure, grid computing capabilities, and fault tolerance mechanisms, provided the core framework for the technical design of the Snap solution. 2 of the major product components within Snap are the JDA Demand Forecaster and the Travel Price Optimization Rate Recommender. JDA Demand is a tool used by hundreds of companies in the retail, manufacturing, and travel and hospitality verticals and provides a host of demand management capabilities. TPO, Carlson Rezidor was JDA's launch customer for the travel price optimization tool. Since its initial implementation at Carlson Rezidor, the tool has also been deployed in various different industries, including several passenger rail companies in Europe, a major golf course operator in Asia, and a global yacht rental company based in North America. Each of these new industries and implementations present slightly different requirements from the core ones associated with Carlson Rezidor's initial price optimization requirements. As TPO's footprint has expanded to meet the needs of other customers in different industries, some of the capabilities so developed have come under consideration for implementation back at Carlson Rezidor. For example, to meet the needs of corporate golf outings and tournaments, and also to assist Carlson Rezidor's group sales desk, a group profitability module has been developed based on TPO. The profitability computation incorporates displacement costs from TPO and ancillary revenues and costs associated with the group business. Carlson Rezidor has a firm plan to implement this TPO-based function in 2012 as a means to guide its group sales negotiations. Now let's look at the next requirement. Carlson Rezidor required a project delivery approach that would provide a progressive return on investment with intermediate milestones, each resulting in some deliverable piece of new revenue generation capability as early as possible. Let us review how this happened. Because Carlson Rezidor was keen to gain insights into its demand patterns first, the implementation of the demand forecasting solution became a natural starting point in the SNAP journey. Once deployed, the forecaster was used to identify low demand periods in need of promotions, to forecast hotel staffing levels, and to provide input to the price optimization prototyping. The prototyping effort constituted a model construction phase followed by a market trial phase. The price optimization prototype was built in AMPLE and utilized CPLEX as a solver. While the core mathematical structure of the model remained largely intact throughout the prototyping, certain business constraints and parameters were refined. For the market trial, test and control properties were identified and price recommendations were implemented in the test set. A year-over-year increase in revenue per available room index, a commonly used KPI in the hospitality industry, was demonstrated, and this demonstration paved the way for product development and system rollout. The success of the prototype led to the test properties to request an extension of the prototyping until such time as the production system was fully deployed. Having ironed out the full requirements during the prototype phase, the product development focused on building robust software that replicated the numerical results of the prototype. Certain aspects of the large-scale production solution were not evident in the prototype and required additional development. For example, the production software required a purpose-built pre-solve capability that was provided by AMPLE but was not available in Concert CPLEX. All the development was conducted using 2-week sprints per the Agile software development methodology. Once the product was developed, the rollout began. A group of properties at a time, first in North America and now in Europe, South America, and Asia. The gradual rollout process has had many benefits, the most significant of which has been the strong advocacy on the part of the early adopters in convincing newer entrants on the value of SNAP. With that, I'd like to welcome Kathleen Mallory to share the benefits of the solution from a user perspective.
Thank you, Suresh. As Fred explained, we have a broad variety of hotels. This means that the hotels also come with a broad variety of people that set the rates at the hotel. We wanted a tool that everyone could learn to trust without having to teach them Pellin's math. We wanted a tool that everyone could find the time to use. And in order to gain internal stakeholder support, we performed a benefits assessment to ensure there was a good return on investment. So how did we gain stakeholder trust? Oh, sorry. There we go. Unfortunately, in 2008 and 2009, the economic downturn meant that year-over-year comparisons for benefits measurement would not be valid. But on the fortunate side, if you're going to test a live rate system, you may as well test it when things can't get any worse. When you can't compare year over year, the next best thing is to look for twin hotels, or at least close enough hotels. We used 20 pilot hotels, different geographies and sizes, to approximate the usefulness to all properties. We accounted for outside influences by comparing test hotels to similar controls in the same region. We held all non-transient segments volume and rate constant, so the unit revenue change would be attributed only to the transient rate recommendations. We tracked rate compliance by having a strict scoring policy. Full credit was only received if the hotel's live rate was exactly what was recommended. To stay in the pilot, they had to follow exact rate recommendations at least 65% of the time. We tested using only a 2-month period, which balanced the need to be secure in the benefits value versus also wanting to quickly start realizing those benefits. The pilot hotels improved their overall room unit revenue between 2 and 4% above hotels that were in the control group. I mentioned the difficulties of testing during the economic downturn. What we observed was that few pilot hotels increased revenue year over year, but they lost at a slower rate, still realizing the 2 to 4% improvement over not using rate recommendations. But to make this money, they had to use the recommendations, and the more recommendations they followed, the more money they made. Based on the forecasted revenue opportunity at 2 months before stay night, and accepting at least 75% of the recommendation, an additional 6 points of revenue opportunity were gained. Blindly accepting all recommendations loses 1 point of opportunity. SNAP doesn't know everything, and so the revenue manager still must address special hotel events. Ease of use was still crucial to tool acceptance. We named the tool SNAP, Stay Night Automated Pricing. We wanted even the name to say it's a SNAP to gain 2 to 4% revenue, but we still needed to make it easy to use. The tool needed to prioritize the work by the highest revenue opportunity and allow the hotel to quickly find and address exceptions. It also needed to be clear and intuitive to set 4 months of rates in 30 minutes a day. The users wanted to know exactly where to find revenue opportunity. So the interface uses a calendar function where the calendar colors point users to important changes. The definition of important is hotel configurable, allowing users some control, ease their anxiety over the perceived notion that they were letting go of setting the rates. Exception management focuses on spending brain power where it's needed, not on dates where nothing in the marketplace changed. Users can configure the screen to display the data that is most pertinent to their property. For example, they can see the previous rate right next to the new recommended rate. Even more important, the elasticity effect is immediately apparent from the difference in the projections of rooms to be sold at either rate. This is something unique to SNAP. We wanted hotels increasing or decreasing demand by rate, not inventory controls. We built screens to review data in a concise and actionable manner. The best part is that SNAP presents this information for the next 120 stay nights every day without fail. And when all this logic still doesn't convince them, we resort to pirates to impress upon them the importance of using SNAP and to help them with training retention. Here's a short clip of training we used at our last Global Business Conference. I introduce Captain Jack Snap.
The name is Captain Jack Snap. Snap! Same name as that thingamabob that magically gives you the best possible room rates day after day. How does it do it? How should I know? I'm a pirate. All I know is this. Anyone who steps up to use it will indeed find hidden treasure.
So it was quite memorable. And now that the hotels have seen the light in consistently using SNAP rate recommendations, we are seeing many hotels with amazing results. 64% of North America properties now use SNAP regularly. 183 hotels automatically publish SNAP rates without intervention. The tool flexibility allows user modification and reload of the rate if they know something SNAP does not. Overall, they are finding that SNAP finds more opportunities than it misses. Our $30 million annual return was based on our conservative pilot results. Recently, as we become more sophisticated in using the power of SNAP, we have observed a few hotels with extreme results, up to 35% year-over-year unit revenue growth attributed to SNAP. We have many supporters. We get comments from hotels all the time. This quote is from Randy Smith at a 65-room Country Inns and Suites in Dothan, Alabama. It is very typical of comments from our hotels, and I believe it is indicative of where we think SNAP can take the revenue at all hotels. So we have now covered all our solution requirements. Fred will now conclude our presentation.
Thank you. For a final word on our work, here is Thorsten Kirschke, our President of the Americas for Carlson Rezidor Hotel Group.
Hello, I'm Thorsten Kirschke, President Americas for the Carlson Rezidor Hotel Group. Today, we're honored and proud. We're honored to join such a prestigious group of finalists for the Franz Edelman Award. And we're proud of the remarkable achievements we've made for our industry with stay-night automated pricing, or SNAP. SNAP is one of the largest and most impactful commercial initiatives we've ever undertaken. This tool, developed in partnership with JDA, is a game changer for the hotel industry. It addresses the age-old problem of pricing a hotel room, which is the most complex and challenging task in the hotel industry today. Therefore, we turn to operations research to advise our hotels on the best price for future stays. SNAP not only sets us apart from the competition, but it has resulted in a quantum leap forward for our hotels. And it has generated some very impressive results. Hotels that follow SNAP recommendations consistently see a lift of 2 to 4% in incremental unit revenue or more on average. Just as important, hotels trust the tool and its flexibility. At our recent Global Business Conference, I heard story after story of how SNAP helped hotels improve revenue performance, including several hotels that saw gains of 20 to 30%. Equally important is that SNAP frees up hotel resources, allowing our staff to deliver a superior guest experience. As one of the largest and most dynamic hotel groups, we are dedicated to innovation and, of course, providing our hotels with the best products. I want to thank Informs for giving us a wonderful forum to recognize this important achievement.
Thank you for your attention.